So today I would like to present my work. It's text generation with GAN Networks using feedback scorer. In this work, I will use text generation approach using conditional GAN, using VGAN, and other things that I would like to discuss. This work based on my thesis, which related to the text generation to NLP. In my thesis, I'm using a little bit another techniques such as Gumbel softmax approach with temperature, but in this paper, I would like to present more simple way to generate text using conditional GAN networks. Controlled text generation can be viewed as a separate topic, especially when we're talking about conversational or chatbot systems, then we have not only text generation task, but also responses from users. And these responses often can be viewed from as feedback, what we can evaluate as in simple form, such as numbers from 1 to 5, and it will simplify our task to evaluate such responses. And we can use this feedback in text generation, improving and polishing our response from our text generation model. GAN networks absolutely perfectly can solve generative tasks for the images, but for text generation, they have some issues. And usually the most important issue, because GAN networks are impossible to get continuous data if it's text, because in text, when we usually use n-gram approach, we add word by word in absolutely separate mechanism. So it's impossible to feed generated text directly to the component of the network, especially if we use LSTM cells inside the network. So there is few solutions how to can overcome this, what I will discuss in the next slides, but here I would like to present a general concept of GAN networks. In GAN or GAN networks. So in GAN networks, we usually have a few components, which is generator and discriminator. Generator, it's part which serve as creator of the content, and discriminator, it's part which evaluates content if it's fake or it's real sample. So for example, the scheme looks the next way. Firstly, we generate some random noise, some latent space, and we feed this space to the generator. After this, generator produce some samples, and we feed the samples with the real samples to the discriminator. The task of discriminator is to decide whether the generated samples is real or not. If discriminator fail to evaluate this, we in backpropagation mechanism, we update loss error and feedback to generator this error rate. So this is basic principle of GAN networks. Solution for text generation task using GAN networks can be viewed as next. The first approach is what we used. It was applying reinforced learning algorithms and policy gradients. And the most famous work in this era, it was generative adversarial nets with policy gradient. Then after discriminator produces its output, we evaluate this output with additional policy gradient. Another approach what can be used to solve this task is a Gumbel softmax approximation. And next approach, what we can say also very important and effective, it's to produce continuous output of generator. And this is exactly what we will do in this work. To produce continuous output of the generator, we'll use autoencoders. And in the next slides, I will show you how we do this. The basic structure of autoencoders consists of two basic parts. It's encoder and decoder. So when we feed input to encoder, let's say the basic example, it's images. Yeah. For example, we input image to the encoder. Encoder compresses data and create compressed representation of this image. The task of decoder from the compressed representation to reconstruct the full image and get the same image as we have in the beginning. So this is a basic structure of autoencoders. Absolutely the same technique we use when we feed text into the autoencoders model. In paper Wasserstein, GAN authors proposed an alternative way to the GAN architecture and training process. Instead of Jensen-Shannon divergence minimization, what usually used in original GAN networks, they use Wasserstein distance, and which has following advantages. Because distance is continuous and differentiable, so we can fit it to the model in the best state. And also using Wasserstein distance, we minimize problem of vanishing gradients problem, which usually exist in GAN networks, especially when we use a really big learning rate. It always happens, so we need to minimize this. Also, using Wasserstein distance in training is more stable. It means we need less change our hyperparameters, and we can define just a few options which will work in most of the cases. And in case of Wasserstein distance, the mode collapse issue happens less often, as author of the paper states, and it's true. But in text task, it's always happens, so we need to discuss this a little bit later, this problem. So scheme of the Wasserstein GAN network almost the same as classical GAN network, but after discriminator, we calculate instead of policy gradient, we calculate Wasserstein gradient distance, and we calculate Wasserstein distance value and feed back this value to the discriminator, and discriminate updates value in generator. Let's move to the next. To control output and generate diverse text, we need to implement our feedback scorer and what we will feed along with the latent space to the generator. It means that we have two inputs of our generator model. So it will be noise and score value. It's need to be mentioned that we need to use the same scorer what we will feed to the discriminator and to the generator in it should be the same value from the same sample. In this work, we will use a combination of autoencoders model along with the GAN architecture. Autoencoders model consists of two parts: encoder which takes our text, initial text, and will learn how to compress this data to vector representation and then reconstruct this data from this vector representation. In our GAN model, we will use this compressed representation of the text. So the basic formulation of the model will look like this. I will not explain in details this formulation because it's basic formulation of GAN networks plus calculation of gradient penalty, which was introduced in the GAN networks paper. I would like to move to the next slide where I introduce the whole model structure. So this is the whole model structure, what I'm using to achieve this task. So let's look in details for this model. Firstly, we have real samples. We have real samples with score value and with text input and feedback value. First, our task is to train autoencoders. We input into autoencoders model our text input without score value, just text input, and train these autoencoders until model will be able to generate stable results and will be able to recognize from the text vector representation reconstructed output. After our autoencoders model completed its training, we move to the GAN training, to the adversarial training. In adversarial training, we use already two inputs. We use our score value and we use our text vector representation. First of all, we pass score value to the generator and also random noise to the generator. After this, generator will produce some samples. These samples, along with text vector representation from autoencoders, it means it's real samples and generated samples, will be fed to the discriminator in the same moment. Discriminator will produce its output with decision, which is real or fake samples, and propagate this decision back to the generator, updating its gradients. So this is a basic scheme of this model. This is algorithm details and with formulation and with steps, but I would like to move to the next slide. In this experiment was used Amazon Review dataset and its a musical instrument subset, which consists of 200,031 samples. But after cleaning this data, I left only 35,000 samples. In the samples, I removed all the sentences longer than 300 words and shorter than 30 words to unify our approach. So the total vocabulary of this model is about 10,000 tokens, which is pretty enough to build some meaningful output of model. For the training was used, and for the full word embeddings was used natural language toolkit library, which simplify our text preprocessing. About the model, we can say that to make a model able to feed discriminator directly, we're using autoencoders with this pre-training, what I already discussed before. In generator, we're using GRU unit to remember states and is as general RNN unit of our network. We could use LSTM model, but GRU has a little bit more stable results, so I would like to use this instead of LSTM model. Discriminator consists of simple layers. It's just convolutional neural network with simple classification architecture. After text preprocessing, we run autoencoders training, and autoencoders training only after already about 10 epochs demonstrated really good results. So as you can see on this image, only after about 8 epochs, we was able to have these results when we have clear reconstructed output from compressed data from compressed vector representation. Need to mention that we use some special token replacement. In this experiment, we replaced start and tokens, and also we replaced all numbers to the one single token. So we didn't use any numbers in this text. In adversarial training, after we completed autoencoders training, we achieve our result in about 20 epochs. And our model started to produce really good output. But there was some experimentation with learning rate because this model faced mod collapse even if we use Wasserstein GAN approach. And this mod collapse leads to that model produces the same output again and again. It means that model finds some output which discriminator think it's looks like real and just stick to this minima. And to overcome this, we need to introduce another concept, what I would like to discuss a little bit later. But decreasing this learning rate, first of all, give us stability in training. We avoid mod collapse. We avoid vanishing and exploding gradients problem. And we were able to generate these samples, what I would like to show. So this is a table of generated samples. I have more samples, but in this slide I can show only 4. So we can see that model was able to generate text using score. We use, in this example, they used only positive score, as you can see, but samples was very well structured. It's so model could learn context. It didn't lose context, so we can say that it really create meaningful and human understandable samples. Using our metrics such as blue score and bird score, we can see that model produces really good output, and but need to understand that blue metrics has a little bit issues in terms of classification text if it has different length and if it has a little bit different context. In the BERT model, we have much better results. What you can see in this in the right column of this table. As conclusion, we can say that we successfully applied feedback score for text generation and got promising results. So we used a conditional GAN approach, we use Wasserstein distance approach, and autoencoders to produce a continuous output for our model. Generated text will structure it and show really great potential to improve this work in future. About problems, what I would like to talk, it's mod collapse, which is like maybe the main problem of GAN network. And there's few approaches to overcome the situation. So first of all, could be used a number of statistically different bins, which was introduced, method was introduced by Richardson and Weiss in 2018. And this calculating this NBD metric during the training, it would be really useful for us to avoid mod collapse, but it will require from us more computational power because during our training steps, we apply some evaluation metrics during the training, which always increase time. And another things how we can solve this mod collapse, it's, for example, if we use Gumbel softmax approach, if you're using evolutionary mechanism, for example, such as EvoGAN or another evolutionary mechanism, then we also calculate additional metrics during the training. But it can become the topic of the next work in the future research. That's all. Thank you. If you have any question, I'm ready to answer.
Dmitrii, I have one question, actually 2. I would like to understand what is this blue score a bit more, and also I would like to understand what are the industry applications of your research.
Mm-hmm.
Yeah.
So you would like to understand what is blue score?
Yeah.
Blue score, it's a model metric which shows how text is close to the human generated text. So how this text is close to the original text, which is a real sample from the real data set.
Okay. So does it use something like cosine similarity or something to compute that? Or?
Yes. So you compare your generated text with original text.
Okay.
Yeah.
Got
And
it.
second question is.
Yeah. Second question is about the application. Where was this applied in the industry?
Yes, this text generation with condition can be applied in any text generation tasks such as conversational agents, such as generation and producing samples with conditions. For example, when you need to generate some not just simple text based on the data, but text with condition. It can be emotion, it can be applied sentiment analysis, it can be applied some classes which you defined in the beginning. So yeah.